There are some natural extensions to k-means that we should cover. One is the fact that if you look at the algorithm, it's quite sensitive to initialization. In order to increase the possibility that we get good results, we can work a little bit on the initialization. We can use the furthest first heuristic to make sure that the centers are fairly far away from each other, unlike the example that we showed in the beginning part of this lecture, where the blue and the red points were fairly close together. What we're going to do is, after picking a first point at random, we're going to pick all of the remaining k-1 centers to be as far away as possible from all of the previously selected centers. This requires a linear complexity calculation where we go through all of the m points in our data set and find the one that maximizes the distance between the closest centroid and the points. Once we've found a point that seems to be as far away from all of the previously selected centers, we're going to select it as the center for the current center that we're trying to initialize. It's easy to see with this algorithm that picking the first point is stochastic, but that the remaining determination is all deterministic. While a deterministic algorithm is often preferable, sometimes a stochastic element is preferable, especially when we are doing some type of ensembling or averaging. So we might prefer a stochastic method. We can add randomness by using this variant, which is what is actually used in the standard initialization in sklearn, which is k-means plus plus. Instead of deterministically selecting what is the next centroid, we're going to choose a point at random, but do so against a probability distribution proportional to the squared distance. So just as before, what we're going to do is we're going to calculate the distance values for each point to all of the existing centroids. Once we have distances for every point, we're going to form it into a probability distribution by normalizing against the entire sum of distances for all of the points. Then we're going to pick a point at random from this weighted distribution. Compared to the furthest first heuristic, which always picks the most distant point, we just are weighting the furthest distant point with a larger probability of selection. Once we've picked a point, we're going to use that as the center for the KF cluster's initialization. One of the big drawbacks of k-means clustering is that we have to choose k, or the number of centroids. This isn't always obvious, as some datasets it may be pretty hard to decide how many clusters a dataset actually has. For example, in choosing t-shirt sizes, we usually have sizes like small, medium, large, and extra large, so maybe 4 classes. But looking at a distribution of people's heights and girths, it's not easy to decide where to cut off. Even after clustering people's measurements against 4 classes, we might decide that a 5th class, petite or extra large, might be something that we could add, or shrink the sizes that we would offer to small, medium, and large. A quick question to ask ourselves to see whether we really understand k-means is whether we think that using the cluster cost by itself, J-clus, as a fitness measure is good by itself. In fact, it's not. And what we'd like you to do is pick one of these 3 options to decide why it might not be a good measure. So let me read it out to you, and then afterwards, please pause this video and select before you go on. 1. There would only be one cluster for all of the points. So k equals 1 all the time if we're measuring by J-clus. 2. It would always output the same number of clusters that I'm already using. So if I decide k equals some number, it's going to end up that way. Or 3. I would have m clusters in total, 1 for each point. Go ahead and pause and reason it out, and then continue on. Indeed, the correct answer is 3. We can see with the cost function that we have, if we have a cluster for each point, each of the points will be exactly clustered correctly, and there will be no distance between the cluster and the point, so we'll have a cost of 0. Because we don't have any penalty for the number of clusters we have, this would get us a lower bound of 0 cost. Obviously, that wouldn't help us at all by saying that all of the points are clustered in their own cluster. That would defeat the point of clustering in the first place. Because of this, we need some way to enforce that k-means finds a clustering that's more meaningful. You can think about this in terms of regularization, where we think that a clustering with all m points as their own clusters would be overly complex, and we'd like to enforce a smaller k to ensure that we get some generalization capability out of it. So what we can do is augment another term for optimization to ensure the value of k is not overly large. There are two popular selections for doing it. One is the Bayes information criterion, or BIC, which augments the cost term with k log n. You can see here, as k grows larger, we have a linear penalty applied to the cost. We also factor in the number of dimensions that are in the data set, but take a logarithm of this. Another popular criterion to augment k-means is Akaike information criterion, or AIC. It's very similar to the BIC, except that it produces a heavier penalty by weighting the penalty twice as much and strengthening the penalty for data sets that have a large dimensionality. So the AIC is a stronger regularizer, especially for high-dimensional data, because of this difference between log n and n.